Today we will continue to explore one sample confidence intervals. Just to recall some of the basic facts here, so let x1, x2, x3, all the way up to xn be a random sample coming from a normal distribution with mean mu and variance sigma squared. We might not necessarily know either of these parameters. We define the sample mean x1 plus x2 plus x3 all the way up to xn divided by n. And given the sample mean, we have the following statistic, the z statistic, which has the standard normal distribution. And we also have the t statistic, which is given by x bar minus mu divided by the sample standard deviation s divided by square root of n. This has the student's t distribution with n minus 1 degrees of freedom. Just to remind you, s squared is the sample variance, and it is given by 1 over n minus 1 times the sum of the squared individual deviations from the sample mean. A one-sided confidence interval is defined either by using an upper confidence bound or a lower confidence bound. So there are various situations where you might not care to know a two-sided confidence interval. And in these scenarios, we calculate probabilities of the type p less than equal to a critical value z alpha equals 1 minus alpha, or the probability of z greater than negative z alpha equals 1 minus alpha. So the former probability gives us a lower confidence bound. We call it L of x, which is a random quantity, and the latter quantity gives us a upper confidence bound, which we denote u of x, and gives us a confidence interval minus infinity to ux. Working with the specific situation where the variance is known, we remind ourselves that the statistic of interest is the z statistic, which is x bar minus mu divided by sigma over square root of n. And alpha belonging to 0, 1 gives us the confidence level, that is 1 minus alpha times 100. Setting up the probability equation now, given by probability of z less than z alpha equals 1 minus alpha, lets us compute our one-sided confidence bound, which is given by the probability that the population parameter mu is bigger than x bar minus z alpha times sigma over square root of n. And this lets us say that with confidence 1 minus alpha times 100, my population parameter is going to lie inside this random interval Lx comma infinity, where L of x is the random variable given by x bar minus z alpha times sigma over square root of n. We can similarly work with the probability equation, probability of negative z alpha less than capital Z equals 1 minus alpha, to get the upper confidence bound. And what it says is that with confidence 1 minus alpha times 100, we will now be able to assert that the population parameter mu lies inside the interval negative infinity to u of x. It's a random interval, okay? And the random variable u of x is defined by x bar plus z alpha times sigma over square root of n. Now, thinking about the situation when the population variance sigma squared might be unknown, the procedure is exactly the same. All we have to now do is work with the t statistic instead of the z statistic, or work with the z statistic under the assumption that my sample size n is large. In each of these cases, we have our confidence bounds calculated as follows. We will next work with prediction intervals for a single future value. The idea being that given a random sample x1, x2 through xn coming from a normal distribution with mean mu and variance sigma squared, We want to predict the value of a future observation that could be denoted by xn plus 1. Uh, the strategy is to use the sample mean as the point predictor. And for the same reasons as we discussed about point estimators, the point predictor is going to be having no measure of reliability attached to it. So, to solve that problem, we will in fact report a prediction interval to gain confidence in our predictor. Uh, the prediction error is therefore going to be the predictor, which is x bar, minus what we want to predict, that is xn plus 1. The expected value of this random variable can be calculated, and we notice that we expect it to be 0. Also, since x1, x2, all the way up to xn plus 1 now is an independent set of random variables, uh, my sample mean and the future prediction xn plus 1 are going to be independent random variables. We can use this fact to calculate the variance of x bar minus xn plus 1, which is the variance of the error. And this calculation comes out to be sigma squared times 1 plus 1 over n. So the prediction error is a linear combination of independent normal variables. Therefore, it is going to be normally distributed with the expected values and variances that we have just calculated. That is normal with expected value 0 and variance sigma square times 1 plus 1 over n. This means that the random variable x bar minus xn plus 1 divided by the square root of sigma squared times 1 plus 1 over n is going to have the standard normal distribution. The denominator simplifies to sigma times square root of 1 plus 1 over n. Working with the probability equation, the probability of negative z alpha over 2 less than z alpha over 2 equals 1 minus alpha, where z alpha over 2 is the critical value corresponding to alpha over 2, we get the following probability equation, which further simplifies to the probability of the random variable xn plus 1 lying between x bar minus z alpha over 2 times sigma times square root of 1 plus 1 over n and x bar plus z alpha over 2 times sigma times square root of 1 plus 1 over n to equal 1 minus alpha. We can use this to define our lower confidence bounds and upper confidence bounds for our prediction interval. And we say that with confidence 1 minus alpha times 100, we can assert that the future predicted value xn plus 1 lies inside the confidence interval lx comma ux. Okay, so note one thing over here is that if sigma squared was unknown, which is usually the case, we can replace the z critical value, that is z alpha over 2, with the corresponding t critical values with n minus 1 degrees of freedom and use the sample standard deviation to approximate S instead. To recap very quickly, we spoke about one-sided confidence intervals and prediction intervals for a single sample. This is all for now. Take care of yourselves, and I will see you around.